da Adnan ti odgovori na pitanje i da prvo pozdravi naravno sve prisutne. Sarajevo jeste nevladna organizacija, mi ovo, da kažem, čisto radi nekog većeg cilja, organizujemo webinare, zovemo predavače, imamo i neke druge stvari u planu, to je nekako, da kažem, dugoročno što se još uvijek treba razraditi. I mi smo u sklopu City AI kao na globalnom nekom nivou, ona nevladna organizacija, na primjer, ona je Wonderland AI organizuju godišnji što bude seminar, da kažem. Mi smo jedan branch, da kažem, samo City AI i eto, trudimo se da malo proširimo i znanje i svijest o data science-u u Sarajevu, što i naravno u Bosni. I hvala ti puno, Adnane, što sam tu došao da pomogneš, da kažem, u tom širenju svijesti. Da više ne dužim, da kažem, s ovim uvodnim govorom. Ena će nam malo predstaviti bolje Adnana, jer Adnan stvarno ima veoma zanimljivu biografiju.
Da, svakako ste mogli preko Eventbrite linka pročitati cijelu biografiju. Mislim, ovo je iskraćena verzija biografije, ali zaista je bogata biografija. Možemo istaći da je Adnan Mehonic, znači, završio prvu bošnjačku gimnaziju, zatim je diplomirao na Elektrotehničkom fakultetu u Sarajevu i tokom svog diplomiranja i cijelog školovanja, da kažem, on je sve neke nagrade dobivao. Evo, recimo, bio je učenik generacije, zatim je bio najbolji student generacije i dobitnik nagrade Zlatna značka Univerziteta u Sarajevu. Magistrirao je na University College u Londonu, gdje je trenutno i profesor na Fakultetu za elektroniku i elektroinženjering, te je on i naučni član Kraljevske akademije za tehničke nauke Velike Britanije. Također je, dakle, i tu dobitnik nagrade Oxford Instruments Award za najbolji magistarski rad. Također je dobitnik i prestižne UCL-ove doktorske stipendije za inostrane studente, te je doktorirao, dobio zvanje doktora nauka za elektroniku i elektrotehniku 2013. godine. I tu je dobio nagradu, njegov doktorski rad je ocjenjen kao jedan od 3 najbolja na fakultetu za elektroniku i elektroinženjering. Također, evo, možete pogledati njegovi Google Scholar i on je autor više od 100 radova objavljenih u prestižnim naučnim časopisima, uključujući i Nature, te na međunarodnim konferencijama. Inovator je 10 međunarodnih patenata, te su osnivač i tehnološki direktor Intrinsic Semiconductor Technologies kompanije za razvoj čipova i sistema umjetne inteligencije. Također je odlikovan nagradom One to Watch, te je i izabran 2017. godine za naučnog akademika od strane Kraljevske akademije za tehničke nauke Velike Britanije. Ono što smo i mi naglašavali na LinkedInu, što je jako interesantno, jeste da ga je MIT Technology Review uvrstio na listu od 35 svjetskih inovatora mlađih od 35 godina. 2019. izabran na poziciju profesora u oblasti nanoelektronike na UCL-u, te vodi tim od 5 doktorskih studenata. Također je i suosnivač, Adnan redovno i doprinosi razvoju BiH društva, odnosno razvojem prirodnih nauka, inženjerstva, akademskog društva, industriju BiH, tako što je suosnivač i predsjednik Asocijacije za napredak nauke i tehnologije u BiH. Pa evo, daću riječ Adnanu dalje, da vidimo šta to ima da nam kaže.
Hvala, Ena. Nadam se da niste zaspali, da vam nije bilo previše dosadno elaborat. Ja sam u konsultaciji sa Adnanom i sa Enom dobio dopuštenje da zapravo prezentacija ide na engleskom jeziku. Razlog je ne toliko što volim da držim prezentacije na engleskom, nego vjerovatno što će mi biti mnogo lakši i efikasniji, jer cijela prezentacija na engleskom, uopće nekako u hodu da prevodim stvari na bosanski. Ali naravno, mislim da je cijeli format ovog druženja dosta fleksibilan, tako ukoliko imate pitanja, slobodno prekinite, pitanja možemo i na bosanskom, odgovorimo mogu na bosanskom, znači čisto samo je prezentacija da ne bi uzeo previše vremena možda da ide na engleskom. Ja samo da provjerim da li vidite moj ekran, to je prezentaciju i da li me još uvijek čujete.
Vidimo, čujemo, sve ok.
Super. Dakle, hvala još jednom na pozivu. Ono o čemu ću ja govoriti je Future of Computing and AI Systems. Vjerovatno većina vas je imala dodira sa umjetnom inteligencijom svakako, a ono o čemu bi ja htio da govorim je nešto malo širi pojam umjetne inteligencije. Dakle, ne samo vezano za algoritmski razvoj, već i za razvoj računara, kompjutera koji su zapravo podrška za sam razvoj umjetne inteligencije i općenito računarskih sistema. Sad ću se prebaciti na engleski. So unless you've been living under the rock, you know that artificial intelligence today is applied for a very wide range of applications. So to name just a few of them, of course, is the autonomous machines. So we talk a lot and hearing a lot about the autonomous driverless cars, but of course, artificial intelligence is applied for much more than that. So all the internet services providers, you know that the Google search is run by these algorithms. But even beyond that, we have the applications in medicine and biology, especially in radiology, for example, that the AI algorithms could be quite useful for the classification and pattern recognition. And then you would be aware of the Netflix and the recommenders that you get to watch the next movie. Of course, all of that is indeed relatable to artificial intelligence and machine learning. But AI is not only used for these, what we could call mundane applications. We do indeed apply artificial intelligence to solve large, complex problems, quite often previously unsolved by the best scientists. So maybe some of you have followed the developments from Google's DeepMind, and this was one of the developments from the last year, or it should be actually 2 years now, that they developed the large AI system that was able to solve the complex problem in biology. That was the open question for more than 50 years, how the certain proteins are folding. So that was indeed quite impressive. And you can see by just these titles that all the world media did cover this story. So indeed, AI has become very big. It is prevalent in the mainstream media. So it's not only something that happens in academic setup or the industry. So what is that actually has fueled the development of artificial intelligence for the last, let's say, 20 years, but even before then? It's basically 3 components. So, of course, we have development of algorithms. So if you are in this field, you would know how this is very timely and active area. But actually, a lot of these algorithms that we use today for these applications have been developed many years ago. So maybe supervised techniques that you might be aware of are developed in 80s, maybe even earlier than that. The other big component that we need to have for artificial intelligence is accessible data. Especially if we want to do the supervised learning, then this concept is based on having vast amounts of data and basically training the algorithms to do something useful. We could say that with the advent of internet, we now have the access to very cheap data, especially for these sort of generalistic applications. The question is, when we have a specific application, like maybe in the medicine, then the access to data might be a bit more costly, and we need maybe sometimes to rethink how do we adjust our algorithms. But the main thing, which in one way was gating the AI for a very long time, was the bottleneck, was basically the hardware development. We had data since 2000s. We had algorithms developed even earlier than that, but then the hardware wasn't really powerful enough to trial and test in practical ways some of these algorithms. So then again, let's try now to twist the story slightly differently. There's another example that was seen as a holy grail of artificial intelligence for many years. So, you know, maybe in the 90s that there was a lot of talk in 2000s about AI of other computers playing chess. Chess was considered to be a very intelligent, creative game that is sort of only dedicated for the humans to be able to play it very well. But then we cracked the problem of chess. That wasn't interesting anymore. And then we tried to extrapolate and to say, what is the next big challenge? And there's this game of Go, which I never played the game, but it is very creative. The possibility space, how you can actually play this game, is vastly more wider than playing chess. So it was considered in the artificial intelligence community to be a very hard problem and something that some people would consider could not be solved anytime soon. But then in 2016, I believe there was the advent of this quite remarkable AI system, a DeepMind AlphaGo system, that was able to beat a human champion in this game. What is remarkable, the first generation of this system beat the human champion, I think 4-1. Then the next generation, which is basically playing against itself, was even better and beat the first generation by 100-0. So it sort of just shows you the progress of the improvement. Once we get to a certain threshold, then the next step is very quick and almost imminent. But the part of the story we don't really hear that often, and myself as an engineer, right, trying to work on enabling some of these technologies, really need to worry about is what are the resources used to run these AI algorithms. So on one side, if you compare the AlphaGo system, you have this huge machine that consists of many computers or chips. So for you who are within the electronic engineering or just generally would know what the CPUs and GPUs are, this system was using thousands of CPUs, hundreds of GPUs, and was consuming around 1 megawatt of power. Now that looks a lot, but then it looks even worse if you compare that against the competition. So the human brain on average consumes a 20 watt of power. So there is some maybe 5 or 6 orders of magnitude energy discrepancy between the two systems. The things are even more alarming and concerning if we consider the training such algorithms. So that could really consume even larger amounts of energy and requires more resources than we have. So you might think, okay, not all of us want to play Go. That's a very specific application. We want to use AI to really do some useful and quite practical applications. So you might consider something which is quite a standard AI task, which is the classification and pattern recognition. So there's this data set called ImageNet, which is a typical one you would use to test AI algorithms on classification. And one quite a famous AI model, deep learning model called ResNet, to train such a model using quite extensive resources, so meaning tens, if not hundreds of GPUs, consumes as much power as 2 weeks, equivalent to 2 weeks of home energy consumption in America. I think this was in the study. So it just tells you that these AI algorithms don't come for free. Indeed, we need to think about the resources. How do we scale up this technology and where all of this is going? Are we approaching the next wall and the bottleneck that will prevent further development of artificial intelligence? So I'm slightly at the risk here to repeat some things that probably most of you already know, but I'm just going to give you a very basic, kind of very quick overview of the most used and common implementation of artificial intelligence, which is the in context of artificial neural networks. So what are artificial neural networks? This is this algorithm that is used in AI today to run many applications. So it's sort of, vaguely speaking, brain inspired. You have this kind of the system that has two main functional units, being the nodes or activation functions that are sort of inspired by the neurons in the brain. And then we have these weights, which are basically inspired by the synapses that connect neurons in biological systems. So it's kind of this is why it's called neural network. It basically looks like a biological neural network. We have these neurons and kind of synapses. And then what happens next is typically in, almost always in NN algorithms, we need to go through two phases. So the first phase is what is called training or learning phase. And that means that the structure of the artificial neural network doesn't change. But what changes is the weights or the values of these weights that connect the specific nodes. So we could use the same structure of the neural network, and just by changing the weights, we can define a certain functionality. So we can go from the functionality of the algorithm recognizing the classes of cats and dogs to, I don't know, having the algorithm that would decide where to steer the wheel to the left or right, to try to drive some small car, right? So this is quite a powerful concept. It just tells you how generic this whole structure is, and just by changing the values of these weights, we are able not only to define the functionality, but also to try to tweak it to get to the specific level of the accuracy. So this is what we do. We basically start with some architecture. We define how many these layers we have, how many nodes, these activation nodes, and then we change these weights until we are happy with the functionality of the network. So how that could look like, maybe basically this NN is the system that has inputs and outputs. You put the input, which could be in form of some display with loads of pixels, and at the output, you might be just interested to say, okay, is this display that I'm looking at, this pattern that comes in the input, is that the dog or cat, right? So then if you train this algorithm well, the algorithm should be capable to infer from that data and to recognize the classes that it hasn't even seen before. So it's not the case it just memorizes. That's not the point. The point is to try to learn something from the experience and then to be able to deduce even for the data sets that it hasn't seen before. Once we are happy with that, we just fix these synapses or these weights, and we are happy with the functionality and the performance of our system. So basically what happens, you then could employ this neural network on any system, you don't need to change anything, and you get this quite a nice functionality. So that's in the nutshell, very, very simplified version of what these artificial neural networks are doing. So it's a black box, we defined the values of these weights, and they do the job for us. Now, going a bit more mathematically, and again, I'm hoping not to go too heavy on the mathematics here, but just to see how do we, the immediate question would be, how do we actually adjust the values? Is there a systematic, robust mathematical framework that could be used so we know how these weights should be changed to define this specific functionality? So we have this algorithm that has been developed many years ago called backward propagation that basically tells us how these weights should be adjusted so we minimize the error. So what is meant by the error is during the training phase, you would show the certain examples of the class, you have the output, and during the training phase, you say to the algorithm if the assumed output or the answer is correct or wrong. So if it's wrong, means your algorithm might not working properly, you need to adjust these weights. So there is a way how to propagate this error signal from the output to the input and basically change the values of all of these weights. So that seems like a quite simple thing to do. There is sort of quite elegant, as I said, mathematical framework behind that. But the one thing that I want to focus on, what is the mathematical operation that we need to do to basically drive this algorithm? I mean, artificial intelligence is not magic. It's basically a very nice algorithm that allows us to do the certain things. But then if we dig in and say, okay, what is specifically what this algorithm is doing, we come to some mathematical operations. And as engineers, you then need to think, okay, is this mathematical operation expensive to be implemented on the current hardware system? And turns out to be that the main mathematical operation that you do is matrix factor multiplication. So basically doing a linear algebra. You need to have some input, which could be the set of these pixels that gets weighted by the values of these weights, these synapses, and you get the output. So that's the main thing you do. In our current digital systems, we like to represent information with the digital values. And we also want to represent everything as the arrays of matrices or the vectors. So this is why we go from, let's say, the equation that looks something like this, to format that looks like multiplication of the vector matrix, and we again get the vector as the output. And this is usually called multiply and accumulate operation. So you sometimes might see that's in short called MEC operation. So now the question is, how many of these operations we need to do? I mean, if I told you, okay, this is the main operation that drives and fuels all of these algorithms, now the question is this expensive to do? And then if it's expensive, how many times do we actually need to do it? So what I put in here are some popular deep learning models. Most of them basically are just doing the pattern recognition. But even in a single pass, a single inference, which means if you put the single data point and that goes through the neural network, then you can count how many of these max operations you would need to do. So depending on the size of the input, you could have the display, which is only 28 by 28 display, or something larger than that, and maybe in some cases even HD display with some very specific cameras. In all cases, you can see that the number of MEC operation is numbered in hundreds of thousands, if not in millions, and typically in billions. So we have all the motivation to try to make this MEC operation as efficient as possible. If that operation is not efficient, it's going to consume a lot of energy and it's going to take an awful long time to get the result. Okay, so this was the sort of the story behind development of artificial intelligence, how we can do these max operation and linear algebra in a very efficient way. And the reason why AI didn't boom, it became huge at the beginning when we had these algorithms. But then sometime around 2010, more specifically around 2012, we recognized that we can use specific hardware chips, GPUs, graphical processing units, to run these AI algorithms in a very efficient way. So what has happened is that we have this era before the advent of the GPUs, or I should say the advent of using GPUs in context of AI, where we see there is a certain trend of the increase in the energy consumption of the AI systems. But then when we realize we can employ GPUs to do the AI for us, well, we became much more ambitious, but also as a direct consequence, we became much more energy hungry. So what these numbers here indicate is the number of weights used in the specific, well, I mean, it's 3 parameters, but you can approximate that with the number of weights that we use in the artificial neural networks. So you can see that something like in 1988, we would have the neural networks with only 20,000 weights. Then in 2009, that's 10 million. But these days, we are really talking about not even billions, but hundreds of billions weights that we use in these more complex systems. So something like AlphaGo uses many billions, hundreds of billions weights to implement. And of course, as engineers, you again would realize this doesn't come for free. There is a very direct correlation between the size of this system, of the neural network, with the energy that you would use. Okay, so let's see the story, the same story slightly differently. You can then ask yourself, what are the computational power demands that we have these days? So what it means is, okay, we know that computers are becoming more powerful and better as time goes on. But then the question is, what is the demand? 2 years from now, what do we think we would need? Is that computer that is 50% better and more powerful than today, or 10 times? So in the past, and I said before 2012, it was the case that this demand pretty much followed what is called the Moore's law. which means that the performance, roughly speaking, of the computer systems would double every 24 months. And basically, the demand and supply was followed. So there is sort of there was basically correlation between the Moore's law and this demand. But then, when we became so ambitious and to employ AI everywhere, this demand increased dramatically. So what happens today is that this demand now doubles not every 24 months, but every 2 months or 3 months, which is really, really quite demanding requirement for our current computer systems. So then you can ask yourself, okay, how do we cope? What happens then? I mean, we have the Moore's law, and for you who might not know what the Moore's law is, it's just the trend that we have. I'm going to come to this anyway a bit later, but it's the trend how our computer systems, and by this we could also mean the mobile phones, are becoming better as the time goes on. And it basically it's related to the efficiency and the size of our transistors. So transistors is the basic building blocks of the whole electronics. So it says if we have a smaller transistors, we can put more transistors on the chips and we have a more powerful chips. So that's the case that this Moore's law was basically saying that every 2 years we can put twice as many transistors on the chip. But it's not enough. As we've seen that the demand, we want to have this doubling every 2 months, not every 24 months. So what we are doing these days, we are trying to implement the smart computer architectural solution. So basically to see, okay, this is what we get from the Moore's law. Maybe it's the improvement by 2x every 24 months. Can I do something with my architecture? So is there some smart way how I could put my chip together to yield me the performance I need? And you see that indeed it's the case that we could improve the performance faster than what we would expect to get only by the Moore's law. But that's not enough. I mean, still, again, I'm going to come to this a bit later. In the last 6 years, we improved by maybe a factor of 300. But then again, if you do a bit of the mathematics, that's not same as saying it doubles every 2 months. So what's then okay, you might think, okay, this all sounds very kind of technical. Why should I care? Well, if you are an economist and if you're thinking about having the company that is somehow dependent on running AI algorithms, then you might ask yourself, what is the cost to run AI? So this diagram tells the story quite precisely, that if we consider the state-of-the-art AI system at that time and what was the cost to train such a system, you can see in 2012 something like AlexNet was a state-of-the-art, and to train such a system cost a couple of dollars, maybe up to $10. But then as we scaled up these systems, the performance improvements that we get didn't offset the size of the models that we had. So today, something like GPT-3, this neural engine that understands the natural speech, is actually costs tens of millions to train. So AI is becoming quite expensive game, right? And the reason behind that basically is the hardware is not improving at rate we need it to improve. So then again, you might ask, okay, forget about GPT-3. How do I do AI today? I mean, I have my smartphone, I use my smart assistants, they seem to work. I also use Netflix. So how does it work? I mean, I don't have the nuclear power in my basement. So how does it happen? So the most used approach today is what is called cloud computing. Actually, the computing or crunching of these numbers or running of the algorithms doesn't happen on our local devices. So you might have the iPhone or this other smartphone that has these smart assistants, and the algorithm doesn't run locally on your mobile phone. What happens? Data gets collected locally, so your voice gets recorded, but then you send all of this data over the internet to the remote data centers where you have much faster, much more powerful computers where the algorithm happens or that this algorithm is executed, and you only get the result. So if you don't believe me, try to turn off your Wi-Fi or go somewhere where you don't have the signal and try to use your smart assistant. Probably say you don't have the internet access. So you might ask yourself why internet access matters. I just want to ask you, I don't know, what's the time? Well, it matters because AI cannot be run on your mobile phone. The mobile phone engine is not powerful enough to run AI in most cases. So then again, you might ask yourself, why should I care? I mean, it seems to work. I'm kind of connected to the internet almost all the time. So is that fine? Well, I think we need to think a bit more. We need to think about the big picture a bit more globally. Is this sustainable? And the answer, simple answer, is no. What we are doing, we are building these data centers that are becoming bigger and bigger and are using more and more energy. So by some estimates, we might get in this situation where 1/5 of the Earth's power by 2025 are used only to run the data centers. So that doesn't seem like a very appealing future. And also, it's not environmentally friendly. There's a lot of these studies that say that training a single large AI model could be just as harmful in terms of the carbon footprint as 5 cars during their lifetime. So obviously, we would like to improve on this, right? It seems that the current approach doesn't quite work, especially if you want to then even scale it up to more complex problems. There's the other reason why we might want to have the system which are more energy efficient and not just to rely on these huge farms of data servers. And this is what's called edge computing. So maybe in some cases you are concerned about the privacy. This especially could be true for the medical application. So you don't want to, I don't know, lend your data to Google or Facebook and say, okay, do the number crunching for me and get me the results. Maybe you're concerned about the privacy of your data. The other one, for many applications, the latency that you get with this cloud computing is quite restrictive. So you might have a drone that flies and then the decision needs to be made very quickly. Do you steer left or right or you crash into a tree? But if you don't get the answer very quickly, and there's always some delay with the internet connections and with the cloud-based computing, that could be quite a big problem. And you might not have the internet access always. I mean, for some parts of the world, they might want to benefit from the AI infrastructure, but they might not have the infrastructure to be connected to the internet all the time. So there is a big motivation to basically try to improve the efficiency. Then you can think about the future. We already have entered the future, what is sometimes called Internet of Things, which means that more of these objects that we in the past considered to be passive are now becoming active or smart. So what does it mean? In the past, you would have the watch, which would be smart one, passive watch that just tells you the time. These days, you speak to your watch, I don't know, you do the shopping or whatever, and you have many objects that are becoming smart. So all of these objects, you have the option either to connect to the internet, and I already told you what might be the issue with that, but also what would be the better approach is to try to improve the energy efficiency. And we are getting more and more of these devices connected to the internet. By some estimates, we already have tens of billions of devices connected to the internet today. You see, there is a lot of talk about this even a few years ago. So this is just a bit outdated keynote presentation from Apple when they presented their new iPhone. Well, that time was iPhone 10. You would notice that maybe if you have followed these events, nobody would talk about artificial intelligence or spend the time talking so much about the chipset that you find in these mobile phones. But today, there is so much talk about AI-specific hardware that you find in every mobile phone, smart mobile phone. And for example, on the keynote for Apple, you would hear about neural engine, what wonderful things it could do, and so on. So there is companies and industry realized long time ago this is really needed. But then again, there's this huge gap in the power efficiency, right? We have the systems which run AI quite well, such as our computers with the GPUs and CPUs that consumes more than 100 watts of power. But then we have these wearable devices and these other kind of applications where we can just have the battery, which is typically less than 1 watt. Right. Okay. So what's I hopefully I presented what the challenge is, what's the problem. So what's the solution? And as I said, well, we have the Moore's law, which is this what is shown here in the image. It's basically the image of the transistor with the source, drain, and gate for you engineers out there, and the size of this transistor. These days, this is 10 times as small. So obviously, Moore's law is still going on, but it's not enough. we have this approach, we just scale up in terms of we build our computer farms and we just build bigger and bigger data centers. But I already told you what the problem with that is. So the next thing we do is the chip architecture, which basically means, are there the ways to construct our computer architecture, the way how do we design computer using these transistors for them to be more energy efficient? So I said about the Moore's law, and it was the case that the Moore's law is still going on, but the rate of scaling down the transistors has definitely slowed down. It's interesting that, Richard Feynman, famous American physicist, who said there is a plenty of room at the bottom, I think back in 1959, where he was talking about the nanotechnology. And it seems that we are running out of space at the bottom, right? These transistors cannot be made to be much smaller than what they are now. Basically, current transistors are made at the nodes, which basically means what's the size, less than 10 nanometers, and down to 7, 5, maybe 3 nanometers. And at that stage, you are getting transistors, which are a chunk of the material, which are made of the handful of atoms, and we cannot really scale it down much further because basically we don't have enough building blocks to do that. Also, the transistors are becoming, we cannot really, what is maybe related to this, in the past we had the case that as we scale down the transistors, make them smaller, they also used to get more efficient. In a way, you have twice as small transistor, it is twice as efficient, meaning it works with the twice, the half of the energy that you would normally need. But that trend stopped a long time ago. This trend sometimes is called Dennard's law. So just for you who might have heard about this one. So what's the game, right? Well, you see now, again, this graph is awfully outdated, but what you have seen that the number of transistors that we use in microprocessors is sort of leveling here. So we're getting to saturation. This trend is definitely slowing down. This Dennard's law, which also could be translated in the frequency of our computers. Maybe, I don't know, maybe some of you in the audience would remember back like 15, 20 years ago, when you would go to buy a computer, you would ask, what's the frequency? Is it, I don't know, 1.6 gigahertz or 1.3 or something like that? And that would make a huge difference in price. Well, since 2010 or 2010 pretty much, it was saturated at around, I don't know, 5 gigahertz frequency. And the reason why we cannot make our frequency go faster, it will basically comes down, it would melt our current chips. They would get so hot, it would melt the material. So the game we are playing, and maybe you have recognized this, is the architectural game, which means we somehow tweak the design of the chips, and this is reflected in a number of cores. So we went from, I don't know, 1, 2, 4, 8 cores to these days 32, maybe hundreds of cores in particular systems. But on the other hand, if we again look a bit more, again, a bigger picture where the bottleneck is, it comes down how our current computer systems are made in terms of just their design. So forgetting about these fundamental technologies. We have what is called Neumann architecture, which basically sees a clear differentiation between the memory and the compute units. So you know, when you have a computer, you have CPU, which is one kind of the chip, and then you have all your memory, which could be DRAM memory, could be flash memory, SSD. There's a method that is actually a separate thing, separate physical thing. And for typically, when you run any application, what happens, you need to transfer this data from the memory to computer back. And this process is actually pretty slow and pretty energy inefficient because we made this differentiation between the computing and memory. And then especially when it comes to the data-intensive tasks, such as artificial intelligence, to move the vast amounts of data, it's becoming so much more energy inefficient and takes so much more time. So this is a very quick example that actually doing computation is not that expensive in terms of the energy. So these are the picojoules. So to do the addition or multiplication doesn't actually cost that much energy. But once you go to fetch the data from the either on-chip or off-chip memory, that costs much more, maybe 2 or 3 orders of magnitude more. So it's all about two things. First, trying to do is, again, going back to these multiply and accumulate operations, to do them efficiently. But the other one is to somehow either to minimize this transfer of data or to make that thing very efficient. The things are even more problematic because it's not only one type of the memory you have. You have actually hierarchy of the different memory technologies. So again, back in the days, you might have used hard drives instead of the flash, these SSD drive these days. And what you would turn on your computer and you would wait, I don't know, a couple of minutes for your operating system to boot up. What would happen? Your non-volatile persistent type of the memory that contains all your operating drives would need to be offloaded to the working memory and back to the processor. So that really was more bottlenecks. It's basically this case of transferring the data from one part of the system to the other that was pretty inefficient. So what do we do? I mean, I said there is a computer architecture, but computer architecture also should be seen in terms of co-designing algorithms and hardware. So this is basically what these big companies are doing. And this is sort of the menu of the chips that you have today. So obviously you have a CPUs, you have something called FPGAs, field programmable gate arrays, which also are used these days. You have the GPUs, which is the main power horse of AI, graphical processing units, and you have what's called ASICs, application-specific integrated circuits. Today, for most cases, what you use is the GPUs. That's what most people are using, and then you have some ASICs, such as you might have heard about the Google's TPU system, Tensor Processing Unit, which is kind of the ASICs specific for the AI applications. Again, depending on you can sort of try to divide the application space. Either you are interested in training or inference, in cloud or at the edge, and to say what particular chip would be the best for that. And then again, there's a lot of marketing that goes to say boost the sales of these AI dedicated chips. So for example, NVIDIA, and then you will hear about how the performance of such a systems goes up by like tens or if not hundreds of times in a short period of time. They would try to do the smart marketing tricks, like call it Huang's law or something like that. So that's all very interesting, and there is indeed the real benefit that you get from this smart architecture that you do. So you might even see in this kind of the graphs that you could try to implement architectures that would not operate only on the matrices and vectors, but on tensors. And for you who might not know what the tensor is, like a simplified description would be a generalized matrix, so something that has more dimensions. And then if you can sort of try to clump more data into these structures, you might have a higher throughput of your data, which would accelerate how quickly you can do these multiply and accumulate applications. But the basic logic or philosophy of developing chips is basically trying to break down this von Neumann bottleneck to somehow to solve this problem. So we have seen how we went from using CPUs, which have only a few cores, if not one core, with some common memory, to these more dedicated chips like GPUs that would have a multiple cores and more shared memory, so there's easier to have a distributed memory in terms of the bottleneck. But then we can ask ourselves, is it possible to then go all the way down and to try somehow implement computing and memory in the same place, or to at least to break it down not in terms of these cores, but individual nanoscale devices. There's also a lot of talk about, can you do something with the reduced precision? So why is this interesting? Well, if you can somehow minimize the amount of data that you need, you could have a big boost. So there's a lot of interesting research that goes on. Can you represent your weights, not with the full precision, which means maybe 32 or 64 bits, but maybe with 4 bits, 8 bits, maybe even 1 bit, and do something useful. And we might get this the energy boosts with this approach, with these smart architectural solutions, and with this approach for a couple more years. But then ultimately, we will need something new. And this comes to the particular research that I'm working on that is very fundamental. So I don't start from building, let's say, technologies from only transistors up, but basically I'm trying to make something from atoms up, to look for in physics of the specific functional materials and to see if there is a way to build more suitable technologies for AI from bottom up. So again, a bit of the, so this is the concept of Memristor. And for you who might never heard about Memristor, don't feel too bad, it's not that popular term, but the Memristor is considered to be what's called the fourth passive circuit element. So you might have heard about the basic circuit elements, such as resistor, capacitor, inductor. And if you took any modules in the electronic engineering, you would obviously know about these. They do connect these some fundamental observables that we have in circuits, in electronics. That's a current, charge, magnetic flux, and which one I'm forgetting, voltage. But it appears there is a broken symmetry. So back like 50 years ago, one scientist called Liam Chua predicted that such elements should exist, and he called it a memristor. So this memristor was a quite interesting mathematical concept, but sort of people forget about this memristor for many, many years. It wasn't really interesting. But then maybe 15 years ago, there is a group at HV Labs that realized that by using some very simple devices, you can realize nanoscale memristors. So you might, okay, still, this probably doesn't resonate with you, doesn't mean anything, but what's the catch? What's so special about these memristor devices? Well, you have this device that looks very similar, like, again, if you have some background in electronics, like a capacitor. You basically have two plates, you have this dielectric in between, and then this is basically like a capacitor, nothing else. So now, the special thing about this capacitor-like structure is if you use a specific materials in between for these dielectrics, you could have a device with adjustable resistance. So nominally, the capacitor should be the open circuit or have the infinite resistance for the DC current. But then if you are careful about what type of the material you're using, you can actually tune the resistance of such a material. So you can get the device, which is called memristor, which basically means resistor with memory, device which you can dynamically change the resistance. So why is that interesting or useful? Well, you can think about the memory straight away. If you can program the resistance of such a device, you can use it for the digital zeros or ones, and that's exactly what the memory is. So then the question, is it better than the memory we are currently using? So we're currently using a flash memory, which is other type of non-volatile memory that doesn't require the energy to retain the state, and you can then see that indeed it is it could go through many more cycles, it's more scalable, it uses less energy, it's much faster, and so on. So it seems to be quite a good memory. And I already told you that AI, a lot of these applications are indeed about the memory bottleneck. So making a better memory, it's a very direct way to improve the performance of AI algorithms. Now, for you who might be interested in physics, I'm not going to really go into many details, but this is basically the structure of such a device. You have some metal layers, you have a dielectric. In our case, I'm using silicon oxide. This silicon oxide could change its resistance by applying the electric field and removing some oxygen ions. What is left, what's called oxygen vacancy. It can then start to conduct a current, and you can basically change the resistance. But the thing you should remember is just a nice device, very simple device that can change its resistance. You can somehow dynamically change the property of such a device. Then you might ask yourself, okay, what is actually, how does the research in this field looks like? Well, it is multifaceted one. You could go from improving the performance of the, let's say, individual devices, and for that you need to do a lot of materials engineering, understanding the solid state physics and stuff like that. So again, this is just a snapshot of some of the research that I do. I'm not going to go in many details, but yeah, it is maybe sometimes in some papers, if you read them, you might see the diagrams, something looking like this. Okay, but let's go to the core thing. So again, let's go back to the max operation. And I told you it's all about how efficiently we can do these max operation. So in the digital system, these max operation on, in general, multiplying matrices scales quadratically. So what that basically means is if the size of the input doubles, or more than quadratically actually, but just let's simplify the things, let's say it's quadratically. If you scale the input by a factor of 2, for example, the time that you would need to wait would go by 4. So you can test this. You can open your MATLAB or Python or whatever, and then increase the size of your matrix and do the inverse of that matrix and see how long it's going to take, right? So then if you need to do this with the large data sets, with these large matrices, it makes lots of difference if this matrix is large or small, or how efficiently you can do that. Now, is there a way to try to do this operation without this quite costly scaling law, without really being dependent on this quadratic scaling? And the answer is yes. You can actually use the memristor devices to do exactly that, only by using two very simple physical laws, the Ohm's law and the Kirchhoff's law. So if you have this kind of grid-like structure, so what you're looking at is basically the lines. It's like a wires or perpendicular conductors. And at the junctions of these lines, if you put your memristor devices, what you can do, you can define the resistance of these memristors, whatever you want them to be. And the resistance values could actually define your matrix. So if you need, let's say, to multiply matrix by the vector, you can define the values of the matrix just by using the resistances as the proxies of the values of the matrix. And then you can apply the input voltage vector. That also you can have arbitrary units here. You just apply different voltage levels. And what you get by the Kirchhoff's law and Ohm's law is basically the multiply and accumulate operation. By the Ohm's law, you get the multiplication because your current is equal to the product of the voltage and conductance. And what you get from the Kirchhoff's law is the summation of these things. So what you got is basically the equivalent of a matrix vector multiplication or MAC operation, which for first doesn't scale. It doesn't really matter what is the size of your matrix element of this crossbar array. It's going to happen in the constant time step. So you basically accelerated the operation a lot. And there is another benefit. You don't need to move your data anywhere. Your data is already there in this matrix. So what you're doing, you're breaking the von Neumann bottleneck on the lowest level. There is no movement of data. Data is there, you operate on data. So this is what's called in-memory compute.
Adnane, izvini što te prekidam, ali imam još takih 5 minuta, pošto nas Google ograničava, pa ako možeš samo...
Okay, fine.
Sorry.
Right. Okay, so I should be quick. And then you can apply this for ANNs, right? The performance of your ANNs, if you do the precise number crunching, you will see it's basically, could go by the orders of magnitude. You need, of course, to think about your algorithms. If there is any device non-idealities that you should consider, and there is always the balance between the efficiency and the performance. So you need to think about that. You can do some smart engineering to actually get what is the most useful thing for you. So I just want to conclude with one more thing. And even beyond these, what we could consider conventional approaches. So there is the other approach, which is quite active and heavy in academia and industry. It's trying to be even more brain-inspired. So what we know about the brain is that our brain, biological brain, doesn't process information with spikes. It processes information, it doesn't process information with continuous signals, but with spikes. Our current computer systems are operating on continuous signals. So you have the constant values of the voltages or currents that you need to process on. But how about if we try to use the spiking-based computing? And this is something called spiking neural networks. They are much more brain-inspired, but they also could be much more energy efficient. And then there is the whole research field that I'm also working on, how to use memristors to implement these what's called neuromorphic functionalities. So try to implement the functionalities we find in the biological neurons and synapses using these nanoscaled memristor devices. So for example, this is the plasticity of the synapses that you could implement with memristors. The other one is a spiking. So you might, I don't know if anybody of you has a background in biology or neuroscience, but you can see how, let's say, the activity from your neurons goes as generation of these spikes, and you can then operate on that. So there is a huge scope, huge interest in doing all of that. So what's then the future of computing, right? At the end, what's the bottom line? So it could look like something like this. We have a digital conventional CMOS. These are the current digital systems. We have something which is currently in development as well, which is quantum technologies, quantum computers, which could be quite interesting for cryptography, for some other optimization problems. And then we could have these analog / neuromorphic kind of systems that could be quite useful for unstructured data, noisy systems, and so on. That could be extremely energy efficient. If you're more interested about this, you can read this in a paper, and of course you can email me to ask about this. This doesn't only happen in academia, right? So this is relevant to the industry. So we'll see how the big companies actually are investing heavily in this kind of technology. So this indeed could be the future of computing. You'll find that IBM, Intels are obviously involved. And with that, I want to